Welcome back again. So, let me continue what I have stopped in the last class. We have introduced the concept of a pressure derivative or a total derivative. A function f from R to R is said to be differentiable at x naught if there is a linear transformation satisfying the certain existence of a limit. Okay. And if not that every function is differentiable, just like in R and you do not get it, but once a derivative exists as a linear transformation, that linear transformation is unique. So, let me just state one theorem. So, you have to understand these results not just by reading the theorem, you work out examples. This is why it is preliminary, we are not getting into the details, work out more details about it. Okay. So, let me state one important theorem here, what is called a before the main theorem we will call it a chain rule. I will not get, we will write a chain rule, let me make it bigger. So, you have chain rule. So, I do not want to give a explicit assumptions etc. Please go and look into the literature for which the references are already given. So, you suppose you have a three sets here F. So, you have your U here, V here, and U is a subset of Rn, and this is a subset of Rm, and this is some Rk in either full set here, and from here to here you have a map F, and here you have to have a map G. Okay. So, F is a map from U to Rm to Rm. So, you can talk about, suppose x naught is a point here, x naught is a point here. So, you want to talk about f prime of x naught, and this x naught going to y naught here. Okay. Okay. So, what is y naught? Y naught is equal to f of x naught. So, you can talk about g prime at y naught. Okay. So, that is nothing but g prime at f of x naught. So, I can compose it. So, I can compose the map from here to here, that is nothing but g composition f. So, g composition f is a mapping from U subset of Rn to Rk. So, I can talk about g composition f, its x naught, what it would be. So, the chain rule tells you that under conditions, of course, you have to make it as a theorem, which I will not do it here. So, you need that f is totally derivative at x naught, g is derivative existence of derivative, then g composition f is differentiable. So, you take your g prime at f of x naught, and then you compose it with f prime at x naught. So, this formula, of course, this is a linear transformation. Keep this, understand that this is a linear transformation from Rm to Rk, you have to understand that. Okay. And this is a linear transformation from Rn to Rm. Okay. That is fine. Okay. So, you see this will be a linear transformation from Rn. So, the x naught, this will act on points on Rm, Rn to produce elements in Rm. So, this when you act on y, it will gives an element here, and but then g prime of f of x naught will act on elements on Rm. Okay. So, it will give you an element in Rk. So, the relation, this chain rule is extremely useful. Now, I will want to give some representation quickly before coming to the theorem. Representation of f prime of x naught, and also is called the Jacobian, which you use it. So, I want to make a distinction between something like that Jacobian of j, this is Jacobian is nothing but I am telling you Jacobian of f at x naught, I will call that. Here before going to the I am going to that only. Before that I want to reduce one more thing, I want another way of writing, another way of writing the same thing you can rewrite in this form, another way of writing of f prime of x naught. Here there is some important subtle point which you have to understand. It says that you look for points nearby, f of x naught has a representation with f of x naught and plus this is the Rm value f prime of x naught acting on h, because this is a linear transformation, plus I write a term RH. This is just not enough. Quite often we may try to write this f of x naught here and they say that this is small. That is not enough. You need another condition, RH should be sufficiently small. Just RH small is not enough. You need to have RH, we call it a small order of h. What is the meaning of this? Small order of h means RH should be in some sense smaller than h. This should go to 0 as h tends to 0. So, if you get an expansion of this form, with RH is equal to something like root something smaller than h, or h is not enough. You have to write this should be in order smaller. Okay. So, then only you will see that you may be able to write f prime of its matrix form which I am going to represent, but that is not enough, as you said existence of partial derivative or directional derivatives may not be good enough to do that one. So, this is another way of writing here. From here I can immediately see this. So, suppose I take Ej, okay, where j is equal to f is from Rn to Rn. In fact, I can do something more general. I can write from more Rn to Rm. Even for that you can write your matrix. It need not be from Rn to Rm. Still f prime of x naught is a linear transformation. Though I have written initially for linear transformation from Rn to Rm, but I am saying that you can take linear transformation Rn to Rm or from other only normed linear spaces. And so, suppose j equal to 1 to n is a basis of Rn. Similarly, you can write down that one here. So, look at this f of x naught, h is a vector here. So, you have to RH, but mod h you have to write it. Okay. So, this is a vector, h is a vector in this higher dimension, h is no longer a scalar, but here I am writing h equal to T E j. Take h equal to T E j. Then apply in this equation, apply in the above equation, you can get it f of x naught f of x naught plus t j. By that formula, it is f prime of x naught plus in acting on T E j, okay, plus R of T E j, where t tends to 0, t tends to sorry, I wrote it t, it is h, I am taking it as h. Okay. So, you have R of T E j. Now, look at this one, this is linear. So, I can write this equal to t into f prime of x naught acting at Ej. Now you take limit by dividing by t tends to 0. If I take this f of x naught plus t E j minus f of x naught by t, what will happen to this term? T I have divided. If I divide that one, I get exactly f prime of x naught E j, and this r t E j by t tends to 0 by my second condition. So, you see, so this is nothing but my partial derivative. So, I can recover all my partial derivatives by the action of my linear operator on the basis element, standard basis element. You can actually compute this, I will leave it as an exercise, can compute not only the partial derivative, you can also compute in any direction of f. So, let me write it, I want to write it here. So, you write here precisely. What is that? That means the existence of total derivatives imply existence of partial derivative. That is what I will say. Existence of total derivative imply directional derivative. Okay. So, that is the thing, but converse you already seen that it is not possible to do that. So, the existence of directional derivative is not enough to obtain the existence of total derivative. Okay. You need some more assumptions on the continuity. Please refer the books to precisely understand. So, what I want to do is that let me write down this df by dxj, at x naught I have f prime of x naught. I want to give a representation now. So, as a linear operator, but recall f is a mapping from Rn to Rm. So, that I can write my f is equal to f1 etc. fm. So, when you look into equations like fx equal to 0, it basically gives you m equations in n unknowns. That is what you will get it eventually. So, now I arrange this. This is actually it is a vector m vector, because m has m component. I arrange it as a column vector. So, I arrange df by dx1. This is a column vector. Df by dx1 is a column vector with m vectors. I do it df by dx2 here up to df by the variable is xn. Okay. So, this column you have m, this will be an m by n matrix, and this is my matrix representation of f prime of x naught. So, I also use my f prime of x naught, which we call it a Jacobian. So, I will call it a, I will not do that. So, this I call it Jacobian of f at x naught. So, essentially all informations are stored. So, this is where you have to be slightly careful. As I said, all dfi by dxj will exist, but it will not give you the linear transformation, because that equation with error term which goes to a small order of h may not be satisfied. So, this point you have to be little, it is this subtle point you should be very careful in dealing with it, verifying the continuity, the additional conditions, additional requirement for the existence of total derivative. You have to be careful and you have to check it. Okay. So, this is how you get, these are all you would have learned it in linear algebra. Whenever you have a linear transformation from finite dimension to another finite dimension, based on its basis you can represent it as a matrix. So, the Jacobian representation, Jacobian is a matrix representation of your linear transformation f prime of x naught. So, the total derivative or a fresher derivative is the linear transformation, its realization through basis is its Jacobian. So, the Jacobian is some sort of a realization of your linear transformation. Okay. So, with that we will go to the inverse function theorem. So, let me go to the inverse function theorem. Inverse as I said, I do not venture into the proof, but I in this another 10-15 minutes there are two theorems which I want to state. I do not know, let me possible to complete, okay, but then let me do it. So, let me give you an intuitive idea and then probably state the theorem. So, you have your function f which is in a neighborhood omega of Rn to Rn. So, the both are Rn, be careful what we are writing, and you want to know the solvability, that is whole issue, right. Solvability, in fact local solvability of fx equal to 1. Okay. So, you have a domain Rn here, this is in Rn, and you have a map here to this is in Rn. So, you may have a point x naught, this is what we are looking at it, x naught, and that goes to a point y naught here. So, the idea is that you want to okay, this is omega. So, you want to look for a neighborhood u and you want to obtain a neighborhood v. This is our aim, I am looking for an aim and this is my v. So, I restrict my f from u to v. So, my question is that can I have such a thing, question f is bijective, I want to do such things. Okay. So, this is my objective, solvability of local solvability. Okay. So, this is what I am trying to do a theorem here. Okay. So, I am going to state a theorem now. This is the I hope you understood. This is what exactly we have done it in one dimension. When f prime of a not equal to 0 and f of a equal to b, and then you have neighborhood of a and neighborhood of b which are intervals, and then f is a bijective mapping. The inverse theorem tells you, and I put condition here, and inverse function theorem tells you the inverse map is also continuous, which I will state it as a theorem now. So, please understand the theorem well and then try to understand the proof. Okay. So, let f as above, let f as above, and okay, a belongs to omega, omega is open, okay, open all that bounded set, all that is not necessary, but open is important, and b is equal to f of a. Instead of x naught, y naught, I am using a and b. Okay. So, I have two assumptions. Understanding assumptions are very, very important. I will explain to you one of the assumption without theorem, without the proof assumption. One, okay, f is a C1 function. You have to be careful what is the meaning of C1 now. I will tell you. Okay. So, existence of derivative is a local point. Okay. So, when I say that function is differentiable at each point, that is one thing, that will not give you C1. So, suppose f is defined in an open interval. When I say f is C1 of AB, I need some continuity of the derivative. So, how do you put that continuity here? That I will explain to you. The second assumption, that is crucial. Look at the derivative only at the point A, exactly y. So, it looks like similar, but now f prime of A is a mapping, linear mapping, right? All right, linear, and you already know that since f prime of A is linear, and I want to see that this mapping is invertible. In terms of matrix, this is equivalent to determinant of this Jacobian, right, that JFA which are right and is not equal to 0. Right. So, f prime of a is a linear operator from Rn to Rn. I want the invertibility of that 1 ontoness and all that, and also telling that determinant of that matrix. These are the two assumptions. Okay. One is C1a. Then the conclusion, let me tell you then, and then I will come back to the then there exists open sets U that is containing A, V that is containing B, which is f of B, A, B equal to f of A, such that exactly what I stated, which I am writing once again. There are two things. One, f from U to V is 1 1 onto. That means the problem, there is a for every y in V which is a neighborhood of P. That is what you have seen. So, you have U here, A here, you have V here, you have B here, this is A, this is B. What it says that for every y here there is an x here, unique x, every y there is a unique x here. Okay. So, let me put it in a red color. So, you have a y here, you have a point y here, you have a point x here, this maps to this point, you see. So, you have a unique. What it says that a second thing, since it is a 1 1 onto, I can define my G equal to, that is my F inverse V to U. How do I define my G of y? G of, so if I take a point x in U, it will go to f of x, and then that G will send that f of x to x back. That is the meaning of the inverse, right. G of f of x equal to x for all x in U, right. That is the meaning. For every x, every v in every point in V is obtained from U by the f, that is what it says. It will be f of x. I am assuming that. So, what is the condition? This is only the definition. It says that is C1 map. Okay. So, that is the theorem. So, I will not, as I say, the proof is based on what we call it contraction principle. Of course, that involves some amount of work, is not easy directly to prove it, but contraction theorem, contraction fixed point theorem, maybe all of you know that. But I want to tell you what is the meaning of f is in C1, that I just tell you, and then I will go to the implicit function theorem. Okay. F is C1 means, so every point x in omega, I can talk about f prime of x, right. F prime of x, which is a where is f prime of x? F prime of x is a linear transformation from Rn to Rn, or linear operator from Rn to Rn. Please understand that. So, I can associate a map from omega to L of Rn, some books you write just L of Rn if both spaces are being, where x going to f prime of x. Okay. And I want, and this is a non-linear space, you can make this to be a non-linear space. and hence there is a continuity. I want continuity of this map, that is the meaning, okay. Continuity of this map. Okay. So, it is not just about the existence of f prime, a mapping x going to f prime of x as a map from omega to L of R n to R n, I need the okay. Now, with this we will go to the final part of this talk, and what we call it the implicit function theorem, and then I will stop it. So, that also requires some work. So, another 5 minutes or so we will do that. Implicit function theorem. Okay. So, what is the setup? So, I am providing a setup and then we will quickly do that one. So, you have an f of x omega. Now, omega is a subset of R n cross R n. So, you have a map from to R n, keep that tradition. So, what does this means? If you have an equation f of x y equal to 0, this basically m n equations in m plus n variables. Please understand that. Okay. So, you have n variable here, n variable. Here you have m variable. So, naturally you cannot solve it. You have only less number of equations than the unknowns. You have an m plus n unknowns, and you can you have only n equations. So, naturally you can only expect to represent n variable in terms of the remaining m variables. Okay. So, it is only so so their question is, we wish to represent x in terms of y. So, you want to solve this such that f of g y equal to so. So, that is what precisely you do it. When you have an x square plus y square plus equal to 1, you want to represent y in terms of x or x in terms of y. So, here you want to represent the n x variable in terms of the n m y variables. So, you looking for this kind of solvability. So, let me look into the special case, linear case, special linear case. Okay. What is the meaning of f of x y is linear? It exactly tells you that you can write it as linear equations like this, a b x y. This is n by n, this is an n by m matrix. So, you get n by m plus n matrix, that is true. F is from R n to R n cross R m to R n is linear, then the metric representation is an n by n matrix. So, this equation, the solvability of linear equation is a x plus b y equal to 0. So, naturally you can solve. So, if A is invertible, that implies you can solve your x is equal to minus A inverse of b of y. So, that is basically your linear form of the theorem. Okay. So, let me so you have the linear form of a theorem. So, I want to do linear version to continue. I want to write down something in a better some other way, decompose my metric. So, let us start with AB in R n m cross n or n plus m, both are fine. Okay, you can write it. And then your f prime at AB is nothing but a linear transformation, that you know, R n plus m to R n. Right. If the same, it is fine. So, let us look at a point HK. HK belongs to R n plus m, which I can write it as HK is equal to H0. This is the operations in R n plus m, 0 k. Okay. So, H is in R n and k is in thing. So, let us look at my linear, this I call it T for the convenience, T my derivative. Okay. So, I can T will act on HK and T is linear. So, I can separate it, T at H0 plus T at 0 k. Okay. I can write like that. So, this suggests me introduce two linear operators, introduce two linear operators Tx from Rn to Rn. This is a linear operator. So, Tx will act on H, H is an Rn vector, is nothing but this is by definition T of H0, this is the definition, nothing else. And another operator Ty from Rm to Rn such that Ty of k is equal to by definition T of this is 0 k. So, the previous thing, thus formally we write, you have to be careful, formally, why I say formally, we write T is equal to Tx plus Ty. This is only a symbolic representation. Okay. So, be careful, T is from Rn, linear transformation from Rn plus m to n, this is Rn to Rn, this is Rm to Rn. This representation meaning is what we have written here. With this, now let me state the implicit function theorem. Okay. So, exactly, so recall f as above, f t, okay, f t as above, a b, you know that f prime of a b equal to t, okay, and then t can be written as Tx plus Ty. Recall all that, whatever just now stated here, where a b belongs to, these are all assumptions, okay, a b belongs to omega, okay, and f of a b equal to 0. So, that is what you look at it, okay, f of a b. So, I want to solve in a neighborhood of b then, okay. So, the first assumption is, this is the with all that assumption, two assumptions are as above, f is C1 assumption, f is C1 of omega, and this part Tx part is invertible. And then the theorem tells you, then let me just state, there exists open sets W which is a neighborhood of B, and U, this is a neighborhood, not a AB, you have to be careful, it is a neighborhood of AB, okay, such that 1 for all y in W, you see, you can solve it, there exists unique A such that AB is in U. You have to state like this, AB is in U, okay, there exists a unique x such that AB is in U and f of AB equal to 0, f of xy, f of xy equal to 0. So, you see you can solve that one. And secondly, I can associate a map now G from W to Rn. What is my map? Where Gy is equal to x. So, that is a unique solution. Again I made a mistake. This will be x, y. We are doing little bit in a hurry because I want to finish it, time is up. So, you have G y in V such that, so this G for which, so the x is y, so that implies f of G y is equal to 0. Okay. And you can also compute my G prime of B, and this map is C1. So, you have G is C1, okay, C1 of W, and G prime of B is nothing but minus Tx inverse of Ty of A. Okay, G prime of this map is. Okay. So, the corresponding component. So, let me finish by just giving a geometric direction, geometric interpretation, that is it. I can't do much here. So, you have a omega here, this is Rn where x belongs to, this is my Rm where y belongs to, and you are given a point A here, given a point B here. So, basically you are given a point A B. So, what this theorem tells you that there is a neighborhood here, there is a neighborhood here, there is a neighborhood here, this neighborhood is your U, this neighborhood is your W. So, you have a neighborhood, and what it says that for every y here, so let me write in color, every y here there is an x here such that xy here, that is what. So, you have a, so y varies along this thing, you will get x varies along you see. So, y varies in this neighborhood of W, x will vary here, but then xy will vary here, and the C1ness of G C1 and the map G is C1 tells you that there is a smooth curve passing through that, and that is a solution to this one, you see. So, that is exactly what you are getting it. Every y in that neighborhood of B there is an x such that xy is in the neighborhood lying, and this varies very smoothly and giving you the solution curve there. Okay. And as I said, all this can be extended, but you get familiarized, we have gone through very quickly, and probably you have to spend some amount of time to getting grasping and understanding this multivariable calculus is extremely important, not just to study partial differential equation, to study many other mathematical part, the analysis of multivariable calculus, studying that in more general setup is important. So, we will stop this here in this. In the next couple of lectures, that is in 1 hour, we will do another preliminary, namely the surface measure and integration. There it is more delicate, I will be only able to give some intuitive picture about it, and it is your job is to learn that thoroughly. Thank you.